Hello again, and welcome to Physics X, Extraordinary Concepts in Physics at Michigan Tech. This almost 15-minute lecture snippet is supposed to be on distance scales in the universe 2, a continuation of distance scales in the universe 1, which you could have clicked on but didn't, or maybe you've seen it. So this will be an interesting lecture where we take you through the universe. First, what did you luck upon here, assuming you're in the internet audience? In this series of small lectures, I'll be going through what I consider to be some of the coolest concepts in physics. So today we're going to do some more on distance scales in the universe, and then, I have another lecture that I'll be recording today on special relativity 1. So this is an actual college course. There are people taking this for credit at Michigan Technological University in the Upper Peninsula of Michigan. The idea is to be light on math, so you won't need to know much math, but to concentrate on concepts. If you want to know a lot about it, then go to the first lecture in this series, which talks about it a lot more. There's no textbook. I'm going to rely on Wikipedia links, which will be in every lecture, and other web links and the lectures only. All right, so there are different scales in the universe. One is if you move over some distance scale in the universe over some amount of time. So if you did that just over distance and time, you get something that probably everyone's heard of, which is velocity. And if you just consider the magnitude of velocity, how fast you're going, you can call it speed. So what is the minimum speed you could go? Well, that would be 0. Or would it be? Turns out that even the concept of 0 speed is somewhat controversial in physics because of the uncertainty principle, which we will cover in detail later in this course. So if you have delta p, which is the change in momentum, delta x greater than or equal to, yes, there could be a 2 pi in there somewhere, but you get the idea, h, which is Planck's constant, some constant, then it turns out that if you know the location of a particle, at least a little bit, then you really don't know the speed of that particle in that direction to some degree. So it could be not 0. So even the concept of something at rest is somewhat interesting and controversial in physics, and that's one of the cool concepts that we'll really get to. What's the maximum speed you can go? Well, whatever speed it is, just go faster, right? So however fast you're running, just run faster, or launch something that's going faster, and you can always go faster yet. Well, it turns out that's not exactly the way it works. There's a maximum speed you can go, which is, as I'll say later, one of the most profound concepts in physics. The maximum speed you can go is called c, which is called the speed of light. And it's not always the speed of light, because if you have the speed of light in air or something like that, it's going to be a little bit slower. So it's really an abstract quantity, the fastest speed. But we call it speed of light and designate it c. Okay, well, velocity isn't the only way you can cover ground. There's something called acceleration. And just like velocity is the change in position over time, acceleration is the change in velocity over time. And it's shown as d2, the second derivative for people who are into calculus. So what's the minimum acceleration? Well, currently it's generally thought to be 0, especially classically. The maximum, sorry, my Google Docs here has a bit of a problem. This should be a larger font. It says maximum unknown. We don't know what the maximum acceleration would be. We don't think it's like velocity. We think you could have potentially maximum acceleration. When you get into particle physics, if you try to do that, though, you might be creating a bizarre amount of particles, and you won't get the acceleration you thought. So I don't really know what the maximum acceleration is. Is that it? Is maximum acceleration the best you can go? Well, actually, no. It's not taught in introductory physics, but if you were to change your acceleration over time, you'd be including something called jerk, which is the third derivative of position over time. And if you were to change your jerk over time, you'd go to jounce. So do you think you run out of them? No, you never run out of them. There's always another derivative. How come they don't teach it? Because it's real difficult to compute fourth derivative, equations, and it's not really all that relevant. You can usually get good approximations without that. Let's say, however, that you had an object sitting at rest. And sitting at rest for more than a 0 time. It's sitting there for a while. And then, after it sits at rest, let's say it then acquires some velocity. How is it that it could have done that? It would have had to have changed, in order to get its velocity, it would have had to have an acceleration for a time. But then, it didn't have acceleration before, so how did it get its acceleration for a time? It had to have had jerk for a time. So, but it didn't have its jerk before, so how did it get that? It had to have jounce for a time. So even just to move anything from rest, at rest for a while, you have to go to all order derivatives, which means that physics breaks down our understanding even if you just try to move an object. And we just get into simple physical approximations just to solve simple things. So, moving on. Okay, I just threw this in there. This lecture is a little bit of a potpourri of different things. Is the universe analog or digital? So I ponder this sometimes. One would think that if everything is analog, then everything is fuzzy if you look close enough. So for instance, if you were to take a line on a page, for instance, a line on your computer monitor, you would say, oh, that line appears crisp. It has definite edges. But if you were to look really, really closely, you would see that actually there's lots of dots on your computer monitor. It's not as crisp as one might have thought. And then if you get even other ideas of fuzzy, what about the uncertainty principle, where if you confine those dots to some velocity or energy or time, maybe it's there, it's only probably different locations. So maybe the universe is sort of analog. But maybe it's digital because everything is discrete if you look close enough. Okay, I got these switched. Things could be digital if they're made up of discrete things like quanta. Like there's quanta of photons. A photon has a certain amount of energy. In string theory, there's a certain string that's doing a certain thing. So maybe things are digital in that way. Which is more correct? And I don't know. It's one of the things I ponder. Even the physical universe isn't clearly analog or digital to me at this time. Planck units. Okay, so before last lecture, we broke units up into seconds, meters, the 4 fundamental kilograms and charge. But in a way, it might be better to break things up into fundamental constants. And when Planck first did this back 2 centuries ago, he tried to compose everything in terms of length, time, mass, and charge in terms of fundamental constants, which are the speed of light, the gravitational constant, Planck's constant, and a constant related to charge. So you can compose anything in terms of that. You can compose speed of light all in terms, you can make any fundamental unit from that. So let's go through these. One of them is called the Planck length. So if you want to create a length, it turns out that you can take the fundamental constants and you can create a length that has meters, but it is, and if you do it in a simple way, it's 10 to the minus 35 meters, which is 10 to the 20 times smaller than the radius of photon. So this is really, really small. Nothing has ever been imaged that small. The significance of this is really experimentally unknown. However, it's thought a lot about in high energy physics and particle physics, and black holes might have a minimum area of an event horizon on the order of the Planck length squared. What happens then, no one's sure because quantum mechanics becomes dominant. Also, when you get into string theory and loop quantum gravity, of which I am neither a string theorist nor a loop quantum gravitist, it's possible that the minimum area that a single bit of information might occupy could be the Planck length squared. So here we're getting into the smallest fundamental distance scales. Okay, another minimum mass is a minimum amount is a Planck mass. So if you take your fundamental constants and you move them around, you create something called the Planck mass, which is 2 times 10 to the minus 8th kilograms in more fundamental units. So the Planck mass is defined when the Compton wavelength, which is, so you have some mass, an electron, and you say, okay, if we took the mass of that electron and made it all into light, energy, what would be the wavelength of that light? That wavelength is the Compton wavelength. And then say, okay, you take that mass, and what is the Schwarzschild radius for that? If you were to condense it all the way down, you were to push on it until it's down to its Schwarzschild radius, what would be that? Then you equate the two. That's when the quantum effects start hitting the gravitational effects, and that's where you hit the Planck mass for that. Now this is not minuscule, because if you were to take a flea and squeeze it down, it has to be a really, really small flea before you would hit the quantum regime. But the Planck mass itself is large enough so that a flea can have a mass of several Planck masses. So it's not a minuscule amount like a Planck length. Let's clear that. Doesn't want to go. There we go. All right. Planck time. This is the time it takes for light, which we know travels at c, to travel 1 Planck length. I had to do a bunch of c to the fifth in order to get time out of there. So if you go back to the Big Bang, if you take the expansion of the universe and you run it backwards, you can linearly say that there's a point at the very center which we'll call the Big Bang. And then you extrapolate from that space-time point and say, okay, if you go out to a Planck time, then we start to be able to understand things better because general relativity will start to work better then. Before that, not really sure what goes on. So the Planck time is the fundamental time that sometimes defines where we're willing to say things about the universe. Okay, so there's a couple interesting scale zooms, one of which is a website, which I will click on, Secret Worlds. I'll maximize it here. So this is a pretty cool website where we'll take you through all the scales of the universe. Please be patient while it loads. Oh, there it goes. Okay. So let's move this here. And let's see. So if you look here, you can see, if you look here, you can see the universe going from the very large to the very small, where the sun is growing large, solar system. We're zooming in on the solar system, then we're going to zoom in on the Earth. It's the orbit of the Earth. Now you can see the orbit of the Moon. Now you can see the Earth. I sped it up. You can go through this nice and slow. And then we'll go to the center of the world, which is Florida. It happens to be on the panhandle of Florida. And then we'll zoom in on this tree, which is not well known, because if we told everybody, everybody would want to go there. And we're going to zoom in on an oak leaf, keep magnifying it as you go in. You can see cells on the leaf surface. You can see the nucleus of the cell. You can see DNA strands in the cell. And they're just lucky enough to start hitting a carbon atom in the cell. And then it takes a while because you hit empty space before you start hitting the nucleus of the carbon atom. And then we hit the, essentially, what is inside the quarks that are inside the carbon nucleus, the protons of the carbon nucleus are essentially as far as we can go in terms of our understanding. So that is an interesting zoom, and there are lots of zooms like this. So let's kill this one and jump to the next page. So one of the earliest concepts of this was in 1968, there was a version called, 1957, there was a book called Cosmic View, where you could flip through the pages. And from that, there was a book in 1968 called Cosmic Zoom, where you could flip through the pages. That's not well known. The most popular one that I know is the 1977 movie, and this is what I saw when I was an undergraduate and younger, and it's called Powers of 10, where it plays interesting music as you go. And so if you go to this page and click on it, you can zoom in, and it will take you, oh, it's best of YouTube now. And I'll run a few seconds of this.
The picnic near the lakeside in Chicago is
and then
we see first the rounded end of Lake Michigan.
The center of the university used to be in Chicago before it moved to Florida. So then you're going to zoom out, and then it zooms all the way back in. So let's stop that one. And a more modern version is Cosmic Voyage, which can be played in 1080p at the resolution of your monitor practically. And so we'll start with that one. And so here, the center of the universe is Italy, and I believe, and the graphics are more up to date, and the larger scale stuff is more up to date. So this shows you all the different scales, and there are certain size scales in the universe that we don't even know much about, slightly smaller than the virus size scale, for instance. There's not much known that exists on that scale, and there's lots of interesting things in the universe. So with that, I will conclude this lecture and conclude with please keep Schrodinger away from your cat. So, see you next time. Almost 15-minute lecture snippet is supposed to be on distance scales in the universe 2, a continuation of distance scales in the universe 1, which you could have clicked on but didn't, or maybe you've seen it. So this will be a interesting lecture where we take you through the universe. First, what did you luck upon here, assuming you're in the internet audience? In this series of small lectures, I'll be going through what I consider to be some of the coolest concepts in physics, and other web links and the lectures only. All right, so there are different scales in the universe. One is if you move over some distance scale in the universe over some amount of time. So if you did that just over distance and time, you get something that probably everyone's heard of, which is velocity. And if you just consider the magnitude of velocity, how fast you're going, you can call it speed. So what is the minimum speed you could go? Well, that would be Hello again, and welcome to Physics X, Extraordinary Concepts in Physics at Michigan Tech, this 15-minute. So today we're going to do some more on distance scales in the universe, and then, well, I have another lecture that I'll be recording today on Special Relativity 1. So this is an actual college course. There are people taking this for credit at Michigan Technological University in the Upper Peninsula of Michigan. The idea is to be light on math, so you won't need to know much math, but to concentrate on concepts. If you want to know a lot about it, then go to the first lecture in this series, which talks about it a lot more. There is no textbook. I'm going to rely on Wikipedia links, which will be in every lecture, be zero. Or would it be? Turns out that even the concept of zero speed is somewhat controversial in physics because of the uncertainty principle, which we will cover in detail later in this course. So if you have delta p, which is the change in momentum, delta x greater than or equal to, yes, there could be a 2 pi in there somewhere, but you get the idea, h, which is Planck's constant, some constant, then it turns out that if you know the location of a particle, at least a little